Here's the link to today's slides. But yeah, how's everyone's week been? Got that extra holiday? Yeah, it's been similar. I guess we'll wait a couple more minutes before we get started. And here's a link to today's slides. Sarthak, do you want to pull up the two poll questions that we had? This one's super important. It's about the future of the music industry. It's monumental. Yeah, I think the thing about reputation is that like the copyright for it expires in 2022. So I think like hopefully that'll be next. That's definitely up there, but okay, I guess we can end this one and share the results. But yeah, it died in 1989. I guess that's to be expected. Okay, the second one is more relevant to what we're doing today. Yeah, sorry, like you want to pull that up? Okay, so today we're going to be talking about recursion. So just share your experience, I guess, with recursion, and then we'll be using that to jump into dynamic programming.
Okay, I'm gonna end it.
Sure. Okay, so some of you have heard of it, some of you haven't. So I think we'll do some quick review and then of recursion, and then we'll jump into dynamic programming. Some housekeeping first. Here's today's attendance code. Call upon V again. So yeah, feel free to note it down or whatever and get those sweet portal points. Here's the tiny URL for today's slides. I dropped it in the chat, so it should be there. I could do that again. Okay. So first, we're going to talk about recursion. And recursion is basically the idea that repeating a task over and over again gets you closer and closer to the desired outcome. Intuitively, you're breaking down a bigger problem into a smaller subproblem. A great way to motivate this is with the factorial. So does anyone want to comment, put in the chat, or either just unmute yourself? How do you define the factorial of a number? Okay, so the factorial of a number is basically, the way I like to think of it is it's the product of all numbers up until a number starting at 1. It's defined only for non-negative numbers, and 0 factorial is 1. So this works really well for recursion because if you think about it intuitively, the factorial of a number is that number multiplied by the factorial of a number that came before it. So what we've done is we've taken a bigger problem and we split it into a subproblem. So if we see 5 factorial is 5 multiplied by 4 factorial, 4 factorial is 4 multiplied by 3 factorial, and so on and so forth. And we'll keep doing this until we reach either 1 or 0, depending on which one we define to be our ground truth. So that's basically the cookbook or the toolkit that we'll use while talking about recursion, and it's more formally known as the base case and the recursive call. So the base case is what we know the solution to. It's usually the smallest subproblem. And quite often, it's either like given to you in the question, or it's just like known to assumed to be known to everyone. But the base case is the most simple, the smallest possible subproblem from where you can't split again. The recursive call is where you have to think. It's not just given to you. This is where you formulate. This is where you think of how you can split the problem into smaller subproblems. Or so in fact, in the factorial case, the base case would be 0 factorial or 1 factorial, depending on whatever you want to do. And the recursive case would be for any other number. The factorial of that number is the number multiplied by the factorial of that number minus 1. So this diagram shows this cookbook applied to like a countdown program. So if the number is less than or equal to 1, that you're done. So that's the base case. And the recursive case is just you're going to call countdown with I minus 1. So in the recursive case, you're splitting it into a subproblem, and in the base case, you're given a solution, so you're done. Okay, so here's something interesting. Always gets a smile, I guess. If you Google search recursion, it says, "Did you mean recursion?" Because it's kind of like you're solving a problem with a subproblem or whatever. Okay, so are there any questions or comments so far? Again, feel free to unmute yourselves. Okay, I'm not saying too much, so I'm going to continue on. Okay, so here's a quick recursion warm-up. So we want to write a program to print the nth Fibonacci number, and the recurrence relation given is f of n is f of n minus 1 plus f of n minus 2, which basically means that the nth Fibonacci term is the sum of the two terms that come before it. Okay, so in this case, what would the base case be? Okay, no worries. So f of 0 and f of 1, okay, wait. Yeah, so for n equals 1 and n equals 0, basically you're going to notice that the formula doesn't really apply because we'd have a negative index, which doesn't really make that much sense. Yeah, so basically the first two numbers are n equals 1 and 2, or 0 and 1 if you're zero indexing, are defined as the base cases because those are the two ground sources of information that you need to write your recurrence relation and to build up from there. So if we know that the first two numbers are 1 and 1, we can start. Okay, so just take a minute or two to think about it, and then, yeah, I think, so we'll take a minute to think about it maybe, and then if you want, I guess, just like type it out in chat, or feel free to just like voice your solution. This is also a great exercise to think about how long a minute is, because I feel like it's been a minute, but okay, I'm going to say it's a minute. No, it hasn't. Oh my God. Okay, whatever. So does anyone want to either like just say what they're thinking of as their solution to uh, like what this will be recursively, or do you want to like type it out in chat? Okay, no worries. So this is a sample implementation that we have. Um, so if n is less than or equal to 0, return 0, and that could be 0 or 1 depending on where you index. If n less than or equal to 1, return 1, and otherwise just add up the two numbers that came before. So yeah, this works, and it's really elegant, it's really clean, it's super easy to understand what's going on. We have our base cases here, and we have a recursive case here. But under the hood, what happens every time you make a recursive call? And I kind of set it out, but does anyone want to either type it out in chat or just hop on, unmute yourself? What happens every time you make a recursive call? No worries. So what happens is basically, oh, someone, yes, thanks, Hartwig. That's an absolute banger. But there's a new stack frame that's created. Basically, there's another function call. And since we're making all of these function calls, what we're going to see is that Fibonacci of 4 gets split into 3 and 2, 3 gets split into 2 and 1, and so on until we hit our base cases. But like we have Fibonacci of 2 appearing twice. We have Fibonacci of 1 appearing a whole bunch of times, and Fibonacci of 0 also appears a whole bunch of times. So not only do we have a whole lot of wasteful function calls, but we also have the same result being calculated twice and we're throwing it away. So how can we fix this? Does anyone have any intuition as to how we could avoid this wastage? Okay, so one way to do it, I guess, would be to have some sort of global data structure where we just store the Fibonacci for every value that we've computed before, and this is called memoization. So what that would do is the first time we calculate the Fibonacci of 4, we kind of evaluate 0, 1, 2, and 3. But then the second time on this branch, excuse me, as soon as we see that we've recalculated the second Fibonacci, we just return that. So that saves us all of the extra function calls that we had on the previous slide. So if you see Fibonacci of 2 appears a whole bunch of times and this splits up again, but now there's no split up after we reach Fibonacci of 2. Okay, so something neat about dynamic programming and I guess recursion is that like dynamic programming, the name was basically invented as like a marketing tool. The whole idea behind that name was that the creator, Richard Bellman, wanted something that just like anyone could understand. So that's something to think about. At the end of the day, marketing and branding is more important than everything else, I guess. Okay, so here's a sample implementation for Fibonacci with memoization. So we have this data structure that we created. We have this nice function. So what we're going to do is we're going to initialize our two base cases. And for every other value, we're going to put a -1 first. And then we're going to call this function. And if there isn't a -1, which means if we've already seen the value that we're at, we just return that. Otherwise, we build it up. Okay, so we're done, right? We have this new data structure, we're saving those wasted calculations. So does this mean we've done all that we can? I guess it's a loaded question because I wouldn't be asking it if we did, but the point is that even though we now have this global data structure memo that we're using to hold all of these values, what we're not doing is eliminating those function calls. So we still have all of these calls to Fibonacci memo, but the only advantage now is that we have this data structure. So we're still doing a lot of recursion. It's just that we're not doing any wasted calculation. And is it clear why that's not a good thing? Okay, yeah. So to continue on with that example, we'll kind of step away from the world of computers and go back to just how we think as people. We're going to reject modernity and embrace monkey. So if you didn't know anything about how computers work, if you didn't know about recursion, how would you calculate the fifth or the nth Fibonacci number? I don't think you'd think recursively, and if you do, honestly, that's pretty impressive. But yeah, basically what you do is you take your two base cases and you build up from there. So when you intuitively calculate the Fibonacci sequence, you're not like recursively doing anything, and you're not like doing a bunch of wasted calculations or creating new stack frames in your brain. But what you do is you just maybe initialize some memory in your brain and just fill in values as you build up. So along those lines, we're going to introduce tabulation. And now what we do is we start at our two base cases, and then we start at the next index. So since our base cases are 0 and 1, we start at 2. And for each next index, we build, we fill it up with the sum of the two values that came before. And then finally, once we reach n, we print n. And now you're going to say, hold on, what really have we changed? Because we still have this like array that we're filling up. We still have these base cases. Isn't it just the same? And that's definitely something, tabulation and memoization, they're a little subtle initially, but what we're doing is, since first of all, everything's in the same function, we're not recursively calling the function over and over again. So that eliminates the recursion. And we're using this data structure, this array, to store Fibonacci values. And what that does is we make sure we're not wasting any computations. Okay, so is that tabulation cleared? Okay, I'm going to take that as a yes, because if it is, that's your first introduction to dynamic programming. Yeah, you should I say it? I won't say it. But yeah, here's a crew meme and something that's very important to have with recursion. You have to make sure that you have your base cases. And since they're probably the easiest thing to think about, it's often helpful to just get your base cases out of the way before you do anything else. So you learn to program, you make a recursive function, and you have no base case, no exit condition. So you keep recursing over and over again. Okay, so let's take a quick break. And then we'll jump into our first warm-up problem, I think. Okay, I think we can take a 2-minute break. Okay, so something natural to think about now is where can we use dynamic programming? And the answer is not everywhere, but there are two things that usually show up in dynamic programming problems, and they're fairly, or it's just something to keep in your mind as to when you should reach for this tool to use. And the first case is when there's an optimal substructure. What that means is, as we were talking about earlier, when you can break your problem up into smaller subproblems, and you can combine those solutions to the subproblems. So what we saw earlier, the nth Fibonacci term is the sum of the two previous terms. So you can break up your problem into smaller subproblems. So that works. And the other case is overlapping problems. So if you're, writing out a solution and you notice that you're doing the same calculation over and over again, then, especially if you're recursively doing that, then maybe instead of calculating those values and throwing them away, you can keep them in some sort of global data structure so that instead of wasting those overlapping computations, you just reuse them and avoid those extra function calls. Okay, so before we jump into the problems, here's a quick summary, another cookbook or toolkit. So if you see a problem and you think dynamic programming is the way to go, first try to break the problem down into smaller subproblems that have the same structure. It's important that they have the same structure so that you can combine the two back to get it back to your solution. So I guess following that, you want to make sure that you can go from the subproblem to the problem, that there is a defined relation that you can use to combine the two. The subproblems are often described as a recurrence relation. That's just, I guess, the mathematical or more formal way of talking about the relations that we've talked about earlier, just like if you can write it out mathematically, that's even better. You're probably home and dry. Okay, so we're going to do a quick warm-up problem. I guess we'll look at it and then split into breakout rooms for a bit. But this is the question. So you're walking up Kuruvangna steps, formerly the steps formerly known as Jan steps, and assume that it has n steps, that n is given to you. So each time you go up, you can either climb 1 or 2 steps. So in how many ways can you climb to the top? Okay, so if our sample input is, if the input is 3, the output is 3. And is it clear how that is? Does anyone want to list out the possible combinations if the input is 3? Okay, so if there are 3, yes. So if there are 3 steps, you can go, you could take 1 and then 2, you could take 2 and then 1, or you can take all 3 one at a time. Thank you for answering that. Okay, so I think, is everyone, does everyone have a sense of intuition on the problem? If so, I think we'll create breakout rooms and we will get back in about 7-ish minutes. Okay, let's see. Yeah, so does anyone want to unmute, share your approach, or feel free to type in chat? Okay. Its pattern resembles that of the Fibonacci sequence, yes. And so something along the lines of, and I guess I'll type this out, but so intuition, maybe like something like f of n is f of n minus 1 plus f of n minus 2. So something along those lines, maybe. Okay, yeah. So this recurrence relation is is the correct one, I think, for this problem. And does anyone want to like talk about your intuition behind why it makes sense, or kind of like how you got there? Okay, no worries. So the way I like to think about this problem is, yes, yes. So basically, if I'm at the nth step, so if I'm at the nth step, where could I have been before this? And so since we can take either one step at a time or two steps at a time, if I was at the nth step, yes, exactly. That's the perfect intuition we got in the chat. So if I'm at the nth step, before this, I could have been either at the n plus one, either at the n plus one, n minus 1th step, or the n minus 2th step. And these are the only two ways of getting to the nth step. So there's no other cases that you have to consider. And what that means is that, so since I have only could have been at the n minus 1 or n minus 2th step, the number of ways of getting to the nth step is just the sum of those two. So the number of ways of getting to the nth step is the number of ways of getting to the n minus 1th step plus the number of ways of getting to the n minus 2th step. Because there are no other ways to reach the nth step since we can't like go down or whatever. Is that intuition clear? Okay, so now that that intuition is clear, I'll take the, the silence to be a yes. It's, I think before we code out, it's super helpful to think about our base cases, and that'll also help us get into a more DP type solution directly. So I think a good base case to start off with is if there are no steps. So so let's think about our base cases. If n is 0, if there are no steps, there's no way of getting anywhere, and we're just stuck. What other base cases should I be thinking of? Okay, so yeah, so the other base case I was thinking of is if n is equal to 1, there's again only one way of getting there, you just take the step. Now, if in our formula has n minus 2, so we might want to think about having a 2 as well. And that's the third base case that I think we need. So if n is 2, how many ways are there of getting there? Yeah, it's 2. Because you can either take the steps 2 at a time or go to the first step and then to the second step. And also, if you notice, for n equals 2, our formula doesn't apply, which is kind of why we have to have a separate base case for it. Okay, so now we have our base cases defined, and we have our recurrence defined. So let's just jump right into it. So I'm going to declare a vector of ints, and I think it's included, so we're chilling. Vector of int, and I'm going to call it numWays. And I'm going to do, I'm going to initialize this vector with our base cases, little cheeky initialization here. Just get those flower places going. So that should be that. Now what I'm going to do is I'm going to loop. So starting, since we have index 0, index 1, index 2 defined, I'm going to start at index 3. So for int I is equal to 3, I less than are equal to n I plus plus. And this would be a great place to ask a clarifying question, or perhaps even before, but I think what I'm going to do is I'm going to assume that n is non-negative. But of course, if there are a negative number of stairs, I guess this question doesn't really make sense because you can't climb downwards. So you could just maybe return like -1 or something like that. Okay, so for the rest of the numbers, we're just going to we're just going to plug in our recurrence relation. I'm going to define a value called ways to current step. And this is going to be equal to num ways sub I minus 1 plus num ways sub I minus 2. Okay, and we have this value, so we're just going to push it back into our vector. So num ways dot push back ways to current step. Okay, and then for our final return statement, we can return num ways sub n. Okay, so this implementation looks good to me, so I'm going to write out a test case real quick. So let's see out. And we can see out climb stairs sub 3. Okay, and we got 3. So it worked for our fairly small-ish test case. We could maybe think of a few more, but I guess we can, before we end this problem, always good to think about what's the time and space complexity of this. And does anyone want to take a stab at it in either in chat or unmute yourself? Okay, so the time complexity of this algorithm, if you see, we have this for loop that's going to run n times each time that we're doing these constant time operations. Yeah, so this is going to be an O of n algorithm, and the space complexity is also of order n because we build up this vector num ways to n. Okay, so I think that's it for this problem. Before we end it, are there any questions? Okay, in which case we can run our post question poll, and I'll switch to the slides again. Okay, that's great to know. Sarthak, do you want to take it away?
Yeah, sure. Okay, cool. Looks like most people found the problem just right, the previous one. The next problem we'll be doing will be slightly harder, but hopefully you can learn some more things. So the next problem we have is longest palindrome. So a palindrome is a string that reads the same forwards and backwards. And we're given a big string, and we want to find the biggest substring, which is a valid palindrome. So for example, like in the ICPC sample string, the longest substring, which reads the same forwards and backwards, is CPC. So basically that's the problem. And I'll give you like about 30 seconds to think about how you would go about solving it. See if this problem has optimal substructure or overlapping subproblems. And then we'll go over the solution. Okay, cool. Hopefully that was enough time for you to like at least digest the question. So let's switch over to Replit and start talking about how to code it. So before we start coding right away, let's go through like some examples. So an example of a string that is a palindrome is the word race car, because if I read it like forwards and backwards, it's race car. And we can confirm that it's a palindrome by checking the two characters at the end and seeing if they match, and then checking the two characters at the next indices from the beginning and the end and checking if they're the same and continuing that way. And if we keep doing that, we'll reach like the center of the word. And if that matches as well, we confirm that it's a palindrome. So this is like a way to check if a given string is a palindrome. And we can do this in O of n time. And so if we use just this, we can run this on every single substring of a string. And there are n squared substrings of a string because you can pick a starting index and an ending index. And for each of those substrings, we can run this an algorithm to find whether or not it's a palindrome. So in n cubed time, we can find whether it's a palindrome. So this is like a brute force solution. But maybe we can like make this better by seeing if this problem can be solved in such a way where we use the solution to a smaller problem to make the solution of a bigger problem. So if we look at this example again, let's say we know that ACK is a valid palindrome. So using that, can we find out whether race car is a valid palindrome? Well, I think we can, because if we know that this is a palindrome, all we need to do is check if the two letters at the end are the same. And if they are the same, that means the bigger word is also a valid palindrome. So we can kind of use like the inner part of the word to check if like the larger word is a palindrome. So we're going from like a smaller solution to a bigger solution that way. So that is like the approach that I'll be using to solve this problem. So the first thing that I'll do is, so I'll be doing this using like tabulation. Like we can either use memoization or tabulation, but I think it'll be cleaner using a table. So first I'll like initialize a table. And it'll be like a table of booleans. So like the way that this will work, like the way that I'm choosing to implement this is I'm gonna say that dpij, so this is like an entry in the table, is true if the substring starting at index I and ending in index j is a valid palindrome.
Sarthak, real quick, there's a question in the chat about spaces.
Okay, so I think in this case, we are assuming that like spaces will be counted as regular characters part of the string. So basically, like if you have palindromic sentences, those wouldn't count. Or hopefully that answers your question. So okay, so that was like what I'm defining DP to be, like an entry in the table for that we'll be using. So then I'll declare the table to be this. Sorry, 1 second. Okay. So before we start like getting into the DP part, I would suggest starting with the base cases. So the base case right away would be a string with a single character, because we know that's the same forwards and backwards. So I'm going to go ahead and make all the entries in the DP table of the form like II to be true. And we'll just do this for like each I. So that's like a simple base case. And another thing that we want to do is have a second base case. And the purpose of this is similar to why we had two base cases for the Fibonacci example, because like the solution of size n depends on the solution of size n minus 2. So like if you have a string of length 2, then that will go to like 0, and we don't account for that base case. So then the next base case I'll do is strings of size 2. And basically here we want to check if the first character is the same as the second character. And if it's the same, then it must be true. So if s at I is equal to s at I plus 1, it must be true. And otherwise, it'll be false. Okay, so those should be our base cases. Does that look okay so far? Any objections? Okay, hopefully it's okay. So the next part is doing the actual DP. So that would mean like filling the DP table, working up from our base cases. So one thing to notice here is like if we want to like fill in the solution for a string of size n, we need to have the solutions to all strings of size less than n. So basically we have to like build the solutions to smaller strings before bigger strings. So what I'm going to do is iterate with this variable called d, and d is like the size of the string that I'm currently working with. And d can range from 3, because that's after our base case of 2, and it can go all the way up to dp.size. So while d is then equal to dp.size, and then we increment d. And then here, I'll go through every substring of size d. So I'll start at I equals 0, while I plus 1, I plus d is less than dp.size. And I increment I. So now I'm checking like every substring of size d starting at I. And so now we can actually use our observation that we can like compare the two characters at the ends and use the solution to the inner word. So what I'm going to check is first, if the inner word, if the letters at the end are the same, then we would use the inner word. Otherwise, we know it's false. So if s at I is equal to s at I plus d minus 1, because like d is a length, so d minus 1 is the index of the last one. Then we set dp at I plus d minus 1 to be dp at I plus 1 and I plus d minus 2. So this is because, we're removing one character from both sides. And if the ones at the end are not the same, then we know that it must be false. So through this process, we basically fill in our DP table and fill it with a bunch of trues and falses. So now that we have our DP table, we need to get the longest substring from it. So basically we want the true value corresponding to the largest substring. And then once we get that, we'll return that substring. So hopefully, if you have any questions, just let me know in the chat, or you can speak up too. But if not, we'll start on the extracting part of the solution.
Oh, real quick, there's a question about line 40.
Oh, okay. So this is just a way to declare like a 2D vector. So I would think that you're comfortable with like Boolean arrays, 2D Boolean arrays. But with vectors, I think this is like the syntax you have to use. It's not as clean. Okay, so does that sound good? Okay, yeah, cool. So extracting solution. So we want to find like the largest substring. So similar to how we were using D here, I'll use D to be like the size of the string that we're checking. And it'll start at dp.size. And we continue while it's greater than 0. And then we want to check all substrings of that size. So similarly, I'll have a variable I while I plus D is less than I plus D is less than equal to dp.size. Similarly, I think this should be a less than equal to. And so now we check if this is true. This substring is a valid palindrome. And if so, we want to, so this is the substring that we found. So we return right away because we found the longest one. So we want to return that substring that starts at index I and has length D. So here we can use one of the string functions. So first you provide the index of a starting point, and then you provide the length of the string. And then, so basically, I think most of the time you'll be returning here, but just for it to compile, you'll have to return the empty string. But most of the time you won't run into this because if you have a string of size more than 1, just that one character is a valid palindrome. Okay, so I believe this is okay. Let's see if it compiles. Okay, so it does compile. Let's try to test it. Sorry. Okay, yeah. So I'll try it on the sample that we were using. Okay, yeah. So I think it returned that the entire string is a valid palindrome. We can also do another sanity check with ICPC. Okay, yeah, CPC. So it looks like it works on the test cases that we tried. Okay, so we have a question. Why is dp less than equal to if in the inner loop it's less than? Okay. Was this the thing that I ended up correcting later? Okay, cool. Yeah, so that's true. So like in cases, we would basically be missing like a case. Yeah, that's true. Okay, yeah, so we can talk about like how fast this would work. So in terms of time, we have like n squared entries in the DP table, and we like update each entry with like a constant number of operations. So the time complexity would be like n squared. And similarly, the space complexity, since this like the size of the DP table is n squared, the space complexity would also be n squared. There are some actually better ways to do this. One thing to recognize is like, let's say we go back to our sample of race car. Like the only time we would use whether or not ACPC is a valid palindrome is when we're checking race car. So like, there's only one bigger solution that we would use this smaller solution for. So by recognizing that, like we could check race car right away and not have to store the solution. So there's actually a solution where you end up using like constant amount of space and still n squared time. And you can do that by checking, by like picking a starting index and checking all palindromes that have that starting index as a center. And you could like iterate through many centers. And that would be like n squared time, but constant space. And I think there's also like a O of n algorithm, but it's like very complicated. But if you want to read about it, it's called Maneker's algorithm. But yeah, if you guys have any questions, let me know. Or otherwise, we can poll. Okay, so I'm gonna release the poll. Okay, cool. Um, okay, so we'll go to our next problem, which will be presented by Katie.
Okay, so I hope you enjoyed the 2-second meme. Right now we're moving on to problem 2. So we're given the coins of different denominations and a total amount of money. We need to write a function to compute the fewest numbers of coins that we need to make up that amount. If we can't make that amount, then we return -1, and we can assume that we have an infinite number of each kind of coin. Sorry, hold on. So let's look at the examples. The first example that we have is coins 1, 2, 5, and the amount is 11. So we can make 11 by having 11 ones, or 5 twos and 1 1, but or 2 fives and 1 1. So the minimum amount would be 2 fives and 1 1, and the output would be 3. Let's look at example 2. We have 2 and the amount is 3. The output would be -1 because we can't make the 3 out of however many 2s, right? And then if we look at number 3, it's coins 1, amount 0, output 0. So that tells us that if the amount is 0, then we can automatically just return 0. Okay, so this is what we have right now. Keep that in mind. And let's go to the, yes, start coding. So what we want to do is I want to paste the question here in case we forget, and also paste the sample input and output here so we can keep that in mind while we're coding. Okay, so what we're gonna do is to first, as you can probably tell, identify the subproblem of this problem since it's a dynamic programming problem. So what would the subproblem be? So the subproblem would be to find the smallest number of coins needed to make up I cents for I in 0 in amount. So now our subproblem would be to build it up, right? So sort of like this Fibonacci number where you find the previous one and the previous two. We should find all the ones that build up to coins, to the actual amount, and we can find the minimal from our previous calculations. So what I'm first gonna do is to have a variable that saves the size of our given vector just for efficiency. And then we're gonna have a vector for ourselves that stores the information. Because for dynamic programming, if we don't store the information, then we can check our previous steps. And the first, if you look at the vectors, the first line is amount plus 1 because we want, because arrays are start index at 0. And we need to go all the way to amount. So that is amount plus 1 elements. And the second one is to fill, let me paste this here so it's easier to read. The second one is amount plus 1 because we need to initialize array before we access it. Otherwise, our evaluation will be wrong because C++ automatically initializes with 0. This would be a problem because we're finding the minimum amount. And if you initialize with 0, then that's the minimum amount. So we don't really have to do any work. So that would be a really huge problem for us. Okay, and then the base case, as you probably may have guessed, is the 0 cents case. So then, yeah, it would be 0. So now we need to traverse through our, right now we need to actually solve our subproblem, right? So then to do that, we can first traverse through our amount. We can start from 1 since we have already solved base case 0. So we can start from 1 and then let's do then the second thing that we need to do is to actually go through the coins vector, right? Or else how would we know the minimum amount? So let's do that. All right. And then inside these 2 for loops, what we need to do is to find the biggest coin that fits the requirement, because that equals the minimum number of coins we need, right? So then the first thing that we need to check is if the coin is less than the amount that we are trying to find, because if it's not, then it doesn't make the case. Okay, so how can we do this? Ideas? It's okay, you're probably just too shy. So what we can do is sort of like what we did in previous lessons, where we compare the stocks lesson, where we compare our current value and the current value is stored in our integer and the current value that we have, and find, whereas the stock we're finding the maximum, this time we're finding the minimum. So what we're gonna do is, for this amount, we have to find the minimum. This is the minimum function. And so we have to compare our current value. This will either be our invalid amount plus one that we initialized with, or a new updated value that was the minimum, right? And we have to keep updating it as we go through the coins list, because maybe there's a bigger coin that fits the requirement, so we can have less number of coins to achieve what we want. So what we're gonna do is compare. The second thing we can compare is the complementary number of coins that we need to fulfill. So this thing is amount I minus coins index is, so say we have, so right now say our, this is coins index is our the element that we're currently in, right? So then if it's less than the amount that we want to find, then there is a number such that the sum of them equals amount I, right? So what we're gonna do is, we do amount I minus coins index. So that would help us find the complementary number, the element that we want. Let's call this element J, just for okay. So this would help us find element J. And then since we have calculated that before, we can just access it from our DP vector. And then plus one, because this is one more operation. We have to actually use the coins, right? The current coin that we're at. So we compare these two values and find the minimum. Okay, finally, we just have to return something. So you might think, okay, let's just return the amount, not spell, return the amount, right? But the problem with that is, see, we initialized our amount here, but we only changed it if it fits the condition. So what if it never did? Then the amount still stays the same. So what we can do is we can first compare value. If this is equal, then it means that our element was never actually accessed, right? So it never fit the requirement, so we can just return -1. Else we can return the actual calculated value that we have. So if you guys are not familiar with this syntax, this is basically this. Okay, so let's check our test cases. So we have 3 test cases that we want to check. For the sake of time, I typed it up already, so I'm just gonna paste it.
Katie, real quick, line 97. I think it should be amount versus a underscore amount.
Sorry. Okay, thank you for catching that. Let's run our test. Oop. Assertion build. Okay, so let's check that. Okay, so I returned -1. Let's go through our problem and look at what happened. Okay, so what happened was, if you guys look at line 99, I said if coins is strictly less than amount I, and that is so seriously not correct, because if coins is equal to the amount, then our answer is just 1. So that was a major issue right there. So let's run it again. Right, so it's correct. Okay, let's uncomment the rest of our code and run it again. All right, so everything works. Let's pass it back to Arjun.
Thanks so much.
Oh, before we, yeah,
Oh,
thank you.
yep, democracy first. Okay, yeah, thanks so much for filling out that poll. Officially, we are done. Here are a few more good problems to do. These are slightly more like involved, and DP is one of those things where a lot of practice helps. But yeah, feel free to fill out the feedback form. It's in the slides. And if you have any questions about the final problem, feel free to stay around. We're here for another few minutes. We'll be here until 8:30 if you want to get any clarifications about that. Yeah, thanks for coming. And another announcement, I think we are off next week, right? Because of the CS32 midterm, so good luck for that if you're in CS32. If you're not, good luck in general, I guess. But yeah, thanks so much for coming. Oh yeah, another important thing that I just remembered spontaneously on my own, completely on my own, is that we have mock interviews. How do people sign up for those? Oh yes, the The link is in the newsletter, and Anna's going to be dropping the link in right now.